Okay, let's jump in the time machine and head back to 1958. We're going to dig into this one single, totally revolutionary paper that honestly helped kickstart the entire field of artificial intelligence as we know it. This is the story of a machine that wasn't programmed, it learned.
So picture this, it's 1958. Computers, they're these gigantic room-sized machines that just follow rigid instructions, right? Step by step. The idea that a computer could have an original thought or, learn from its mistakes, that was pure science fiction. But then this psychologist, Frank Rosenblatt, comes along and asks this totally radical question. What if we could build a machine that learns not from code, but by actually mimicking the way our own brains work?
You see, before you can even think about building an artificial brain, you've got to have some idea of how the real one works. And for Rosenblatt, that meant tackling one of the biggest mysteries in science. How does the brain actually hold onto information? At the time, it was a complete black box. This was the big one, the central question. When you learn something new, a face, a name, some random fact, what is physically happening inside your head? Back then, neurophysiology didn't really have a clear answer, but there were two major competing theories floating around. So this is the core of the debate, right? You've got two big ideas. Is memory like a file in a cabinet, neatly stored away in one specific spot, and you just pull out the file when you need it? Or is it something way more chaotic? Is it just a pattern that emerges from all the connections between our brain cells? Rosenblatt, he went all in on that second theory. He believed memory wasn't a thing, it was the web.
All right, so armed with this theory about how memory works, Rosenblatt set out to design not just a new kind of computer, but a whole new kind of machine.
We really have to stop and appreciate how huge this shift in thinking was. Computers calculated, they followed commands. They were incredibly powerful, sure, but they weren't creative. Rosenblatt wanted to build something that could actually form an idea all on its own. And he gave it a name, the Perceptron. Now, think of it as a hypothetical nervous system. The really crucial difference? You don't program it to do a specific task. Nope. You design it to learn that task from scratch through trial and error, and that right there is a core principle that's the direct ancestor of the AI in your pocket today. And this diagram from his original paper just illustrates the basic concept so brilliantly. Now, it might look a little complicated at first glance, but the main idea is actually a pretty simple three-stage flow of information, and it's all designed to mimic how our own brains might work. So let's break it down. So how does this thing actually tick? Well, it all boils down to a really simple three-part pathway: sense, associate, and respond. Okay, so first up, you have the sensory stage. Think of it like an electronic retina, a bunch of light sensors that see an image. Simple enough. Then comes the association stage. This is the cool part. The signals from that retina shoot over to a big web of artificial neurons. And here's the key. At the start, all those connections are totally random. Finally, you get the response. Based on which of those neurons get activated, the machine spits out a final answer. But what happens if it's wrong? How does it actually learn? And this is the secret sauce. Learning happens by changing the strength of the connections. When the machine gets an answer right, the pathways that led to that answer get a little stronger. If it gets it wrong, they get weaker. It's not rewriting code, it's physically changing the network itself, a process that happens billions of times a second when the AI in your life learns to, say, spot a spam email. I love this analogy, it's just perfect. Think about paths in the snow. The very first time you walk it, it's tough. But every time you walk that same path, the groove gets deeper and deeper, right? It becomes easier and easier to follow. That's exactly what's happening here. Every time the Perceptron gets a guess right, it's like taking one more step on that snowy path. Eventually, that path becomes this super defined trail, and that becomes the default route for the signal. The network is literally teaching itself which pathways work. So the theory was elegant, for sure. But the big question was, would it actually work? Rosenblatt had to put his machine to the test. So using simulations on a super powerful IBM 704 computer, one of the beasts of its day, Rosenblatt gave the Perceptron a really fundamental visual task: just tell apart simple geometric shapes. It was shown hundreds and hundreds of examples, and with each one it got feedback. Yep, that was right, or nope, try again. And that allowed it to start reinforcing the correct pathways. And the results? Honestly, they were just astounding. I mean, the machine starts out just guessing, right? It's got a 50-50 shot, a coin flip. But after a bit of training, whoa, its performance just skyrockets to near perfect accuracy. It had actually learned to tell the difference. But believe it or not, the most important test, that was still to come. This right here is the true hallmark of intelligence. I mean, it's one thing to memorize the exact squares and circles you've already been shown. It's a whole other thing to recognize a brand new square, one that's maybe a different size or in a different spot that you've never ever seen before. That's called generalization. And this is exactly what the perceptron could do. It could correctly identify new shapes it had never encountered. And that proved it hadn't just memorized a bunch of images. It had formed an abstract concept of squareness. It had learned the idea of what makes a square a square. This was the real breakthrough. That moment a machine showed a tiny spark of the same kind of intelligence that lets your phone recognize your face from any angle. So Rosenblatt's 1958 paper wasn't just some successful experiment. It was a proof of concept for an entirely new way of thinking about intelligence itself. These were the big takeaways, and you know what? They're just as relevant today as they were back then. Rosenblatt proved that a simple brain-inspired network could learn, it could remember, and it could generalize, all without anyone programming it step by step. He showed that memory could be spread out across a whole network, and that real order could emerge from a completely random system. So why does any of this matter today? Well, here's the kicker. Those fundamental principles of the perceptron, learning by making connections stronger in a network, those are the exact same principles that power the massive neural networks we have today. The AI in your phone's camera, the systems that help doctors diagnose diseases, the legacy of this one paper from 1958 is quite literally all around us. The perceptron proved that a machine could learn to see. It was a simple, beautiful, elegant first step on this incredible journey. And when you look at just how far we've come since 1958, the real question is, where do we go from here?